In this video, we're going to talk about the seventh factor which affects acidity, and this is aromaticity. Now, this is probably the most obscure of the 7 factors we'll talk about that affect acidity, because you won't generally encounter it until you get to the subject of aromaticity, which isn't until you get somewhat into your study of organic chemistry. It usually comes later on. But the bottom line, what we need to just talk about for this video, is it's actually going to fall into a lot of the same rules that we've talked about earlier. And the key thing to know about this is just that aromatic molecules are unusually stable. And we won't talk about how to identify an aromatic molecule. That's a whole other series of videos in itself. But just we'll assume that you can recognize what an aromatic molecule is, or I'll just tell you that it is aromatic. And from there, we're going to use the same principles of acidity and basicity we've talked about before and understand why it is that it affects basicity and acidity. So aromatic molecules are unusually stable. And if you remember, we were talking about before that the strong acids have weak conjugate bases. Another word we could use for weak is stable. Pretty stable conjugate bases. So if the conjugate base is stable or unusually stable, then we would expect that, or if it's aromatic, then the conjugate acid would be unusually acidic. Okay, so let's just tell you what I mean here. So let's start off with a molecule like, this is not an aromatic example, by the way. Let's start off with this molecule here, and let's just say that we have a double bond, and it was to lose a proton, so spontaneously lose a proton. This doesn't happen in real life, but we're using this to illustrate the stability of conjugate bases so that we can sort of understand this a little bit better. This is a very unstable molecule. How unstable? It's a little bit more stable than if it was just cyclopentane because of resonance, but it's extremely unstable type of molecule. This would not be a very favorable type of reaction. When we discuss pKa's, we'll go into a little bit more detail and talk about how we can actually assign a number to some of those things. It actually has a pKa of 43 in that ballpark. So if we, instead of having one alkene present, if we actually have these 2 alkenes present, now this molecule turns out to be aromatic. So this conjugate base here is unusually stable. Unusually stable. So how would we expect this to affect the acidity of these molecules on the left? Which of these 2 molecules do you think would be more acidic? The one that gives us this unstable conjugate base on the top, or the one that gives us the fairly stable conjugate base on the bottom? Well, you'd expect that this reaction on the bottom would be more favorable. More favorable, right? Because we're going to go to a more stable product. And this would be much less favorable. Which means that this is going to be a stronger acid, and this is going to be a weaker acid. Much weaker acid. So again, it sort of ties into the factors we were talking about before, and that is that anything which can act to stabilize the negative charge in the conjugate base is going to make your conjugate acid more acidic. And aromaticity is just another factor which can lead to stabilization. And so therefore, if your conjugate base is aromatic, the conjugate acid is going to be unusually acidic. And it turns out that this is almost as acidic as water, it turns out, this molecule here. Later on we talk about pKa. We're just about to talk about that. pK of about 16, which is close to 17. It's close to water. It's almost acidic as water. Amazing. And this is a pK of about 43. We'll talk about that as extremely weak acid. So this aromaticity is a really, as we'll learn later, is a really big deal in terms of being able to stabilize molecules. So again, bottom line, conjugate base is conjugate base is aromatic. It's going to stabilize the, it's going to make the conjugate acid a stronger acid.